switch off my camera now?
You can switch off your video or you can keep it on, whichever would make you happiest. In the meantime,
yeah, so I can switch it off.
okay.
So questions, I will switch it on again.
Okay, very good. So we are delighted to have Asmita Mukherjee here to speak to us about probing matter in 3 dimensions. Asmita received her PhD from the Saha Institute of Nuclear Physics in India. She then held postdoctoral researcher positions at the University of Regensburg, I'm pointing at Herbert here, and the University of Dortmund in Germany, and at the University of Leiden in the Netherlands. In 2005, Asmita accepted a position in the Faculty of Physics Department at the Indian Institute of Technology Bombay, and has been a professor there in the same department since 2015. Asmita has been a Humboldt Fellow at the University of Tübingen, Germany, which is through the Alexander von Humboldt Foundation, an exceptionally high-profile honor, and a Serb Power Fellow through DST Serb India. So we're really honored, Asmita, for you to take the time to speak to us today, and we really appreciate it. Please take it away when you're ready.
Thank you, Will, and thanks for the kind invitation. It's an honor to give these talks for the students and faculty and postdocs and staff of Cape Town University. So I have never been to Cape Town. I hope to be there at some point. But
we have
today,
TIS March.
yeah, why not? So today I will give a short introduction on the subject area of my research, not really getting into the research problem, but rather a broad overview. So I am sure there are experts in the audience, so it's mainly intended for students. So I work in the field of probing matter in 3 dimensions. It is QCD, which falls in the area of high energy theory. So as we all know, the standard model of particles. So this is a list of all these standard model particles. We have these quarks. There are 6 quarks, quarks of 6 different flavors, the up, down, charm, strange, top, bottom. Then there are these leptons, electron, muon, and tau, and the corresponding neutrinos. So here in red, there are the force carriers. So these particles interact through electromagnetic, strong, and weak interactions. So strong interaction is mediated by the gluons, which is a massless particle, and it is electrically neutral, but it has a different kind of charge called color charge, same as the quarks. And the electromagnetic interaction is mediated by photon, and it is massless, it is charge neutral, and the weak interaction is mediated by Z and W bosons. And then particles get their mass through spontaneous symmetry breaking through Higgs mechanism. So all of us know about this. So in this talk, we will be basically concentrating on the strong interaction. So structure of the nucleons in terms of quarks and gluons. So the fundamental building blocks are these quarks and gluons. So that they basically appear inside these atoms. So, so matter is built up of these atoms. So at the center of this atom, there's this nucleus and the electrons rotate in orbits around it. So the size of these atoms, you can say approximately 10 to the power minus 10 meters. So this nucleus that lies inside the atom is of the size 10 to the power minus 14 meter. And these nucleus is made up of these various nucleons. So there are 2 kinds of nucleons, they're protons and neutrons. So the size of these nucleons are approximately 10 to the power minus 15 meters. And these nucleons are also not fundamental particles because there are quarks, antiquarks inside these nucleons. So there are these 6 different kinds of quarks, they're corresponding antiquarks, and they exchange gluons. The size of a typical quark is very small. It is even less than 10 to the power minus 19 meter. So when I am talking of size, we actually do not put matter under a very powerful microscope and really probe these kind of sizes. That kind of strong microscope is not available. So these sizes or the distance scales are basically inverse to the energy scales. What I mean is that in order to probe this quark-gluon nature of this matter, you have to probe the system at this kind of distance scale or the corresponding energy scale, which is very high. There are various unanswered questions related to the quark-gluon structure of matter. Several of them are listed here. For example, whether quarks and gluons, how do they move around inside the volume of the nucleons? Do they have transverse momentum? And if so, do their transverse momentum somehow interact the spin? What if the proton is polarized? Whether there is a transverse momentum of the quark interact with the polarization of the proton? What about their orbital motion? Do quarks and gluons, do they have orbital motion? How do these quarks and gluons are distributed in the space? And then most importantly, how is the nucleon mass formed from these quarks and gluons? So these are some of the fundamental questions that people working in this field are trying to understand. So this is a very nice slide, which I borrowed from, or actually stolen from Abhay, because I like this slide and the example. For example, you want to study the internal structure of a watermelon. There are two ways to do it. First of all, you smash two watermelons against one another with great force. Okay, so the watermelon breaks up, as you can see in this picture, and you can see the inside of this watermelon. So you can give this, and so this is somewhat analogical to what is being done in high energy proton-proton or heavy ion collisions. So these kind of experiments are being done at Large Hadron Collider and at Brookhaven, RIC. So you smash two heavy ions against one another at very high energy. The ions break up, or you smash protons against one another, the protons break up. And looking at the debris, the final states, you find some idea of the structure of this matter and these interactions. The second way to find out about the structure is not to smash the watermelon, but rather taking a knife, as this guy is doing here, and cutting the watermelon into slices, like thin slices like this. Here, you get two-dimensional images, multiple two-dimensional images of a three-dimensional object. So this is what is done in tomography, right? Tomography is reconstruction of the structure of a three-dimensional system in terms of multiple two-dimensional pictures. So this can be done. The analogy for this is a high energy deep inelastic scattering, that is an electron-proton collision. So electron is a point particle. So you can collide very highly energetic electron and proton. And this, as we are going to see later in my talk, this will be basically something like getting multiple two-dimensional images of the proton. So there are various experiments around the world which probe matter at high energy by bombarding particle beams at high energy. One of them is at Large Hadron Collider at CERN, Geneva. This is a aerial view of it. So it bombards heavy ions and two proton beams head on. Then there is the relativistic heavy ion collider at Brookhaven. So it also bombards proton beams or heavy ion beams. This is Jefferson Lab. This is a fixed target experiment. So one bombards a highly energetic beam on a fixed target. And this is actually DAISY Hera, which has concluded its operation now. This was in Germany. So there is also an upcoming experiment coming up at Brookhaven. So I'll discuss about that. Now, what happens when you collide a very highly energetic electron with a proton? So what happens is that this is an example of inelastic electron-proton scattering. The proton, when bombarded by the electron, loses its identity, it breaks up. Okay, so you bombard this electron with the proton. So this electron interacts with the proton through the exchange of what is called a virtual photon. So this is a photon which has sort of a mass which is given by q square. So this proton breaks up and you do not care what happens to the proton. You do not measure the final state debris. Rather, what you measure is that you measure the scattered electron. So if the instant electron has an energy E, so the scattered electron will have some other energy E prime, which is E minus nu, and theta E is the scattering angle. So nu is basically the energy that is carried into the proton. So nu is q square by twice m, where m is mass of the proton. So you can calculate this differential scattering cross-section, and this differential scattering cross-section, that is cross-section differential in the solid angle of the observed electron is written in this way. So the advantage is that it basically factorizes in terms of a point particle scattering cross-section, which is given by the sigma mod times some part which depends on the internal structure of the proton. As I said before, proton is not a fundamental particle. It has some structure in terms of quarks, antiquarks, and so on. So this structure is included in these quantities, which are called W1 and W2. These are called structure functions. So this structure dependent part of the proton somehow factorizes from this electron part. So this is another picture of this deep inelastic scattering. So this scattering, so in the previous slide, what I discussed was not actually a deep inelastic scattering. You can call it inelastic scattering. The scattering is called deeply inelastic or deep inelastic in this kinematical region when the virtuality of the photon is very high or almost infinite. I forgot to mention that the photon exchange have to be space-like in DIS. So this virtuality is very high, but the x, the variable x, which is q square by p twice p dot q, is fixed. In this kinematical limit, what happens is that virtual photon does not interact with the proton as a whole. Rather, it sees the partons, or it is a common term for the quarks and gluons. It sees the partons or quarks inside the proton. So this is the picture that we have now. You have highly energetic electron and proton beam bombarding against each other. So in this highly energetic system, the proton basically to the electron looks like a pancake. It is Lorentz contracted. It is a pancake in the transverse plane. And the target, that is the proton, can be thought of as a collection of partons frozen on this transverse plane. That is, these partons are moving along the direction of the motion of the proton, and each parton you can assume can have a different momentum fraction of the proton. Usually this is called x, and this x is the same as this x. So each parton or quark carries a momentum fraction x of the proton and moves in the same direction as the proton. And we assume that in the transverse plane, they are just frozen. So what is the idea behind this assumption that it is frozen in the transverse plane? So in the deep inelastic limit, the electron passes the target almost at zero time. It passes through the target very fast. And that is why it sees partons frozen in the transverse plane. However, the electron or the virtual photon can interact with the partons only if the impact parameter is less than 1 by q. That is basically the momentum or length scale. Electron parton scattering happens at a much shorter time scale than the hadronization scales of the proton remnants. So in this limit, the partons with which this photon is interacting is assumed practically to be free. So I'm coming back to it again. So in this limit, the deep inelastic scattering cross-section can be written like this. It is again a factorized form. So it is a factorized form of a differential cross-section between the virtual photon and the parton, that is quark-photon interaction. And it is an elastic electron-parton scattering. And there is an incoherent sum over all partons. So inside the proton, there are many quarks, antiquarks, and so on. So we have to sum over all partons because we do not know which parton will interact with the photon. And then this is the charge of the quark. And then this is what we were seeing in terms of the structure functions of the proton. So now we will call them parton distributions. So this is basically probability density of finding a parton of momentum fraction x inside the proton. Okay, so the virtual photon interacts with the parton, and then there is a probability density of finding a parton of momentum fraction x. So in parton model, which was first put forward by Bjoken and Paskos in 1969, partons were assumed to be non-interacting based on the argument that I discussed in the previous slide. So this is a factorized form of the cross-section, and the factorization of the hard part from the soft part. So this parton interaction with photon is a hard part of the cross-section. So by hard, we mean that it can be calculated perturbatively order by order. And this part, the probability of finding the parton with momentum fraction x, this is called the soft part. So parton distribution is in the soft part of the process, and parton distributions cannot be calculated perturbatively, rather it is a non-perturbative object. So this factorization is incredible because another thing that is noteworthy is that this hard part, that is interaction of partons and the virtual photon, it depends on the specific process. Okay, there can be different kinds of interactions. So these interaction, parton-photon interaction, one has to calculate process by process. But this parton distribution is independent of the process. So once you obtain this parton distribution by fitting data or extract them from experiment or parameterize them, you can use the same parton distribution to predict the cross-section of another process. Okay. So again, I have to explain it a bit further. So this gives the predictive power of this theory. Now, so initial experiments suggested that parton distributions are indeed functions of X. However, later experiments showed that that is indeed not true. So in addition to X, there is also some dependence on the scale Q square. So this is called scale evolution. And actually, it was found that this scale evolution can be calculated using what are known as evolution equation of partons. In order to explain the scale evolution of parton distributions, one had to forget about this assumption that partons are actually free, because parton model assuming free partons does not give this scale evolution. Scale evolution occurs when quarks interact with each other via exchange of gluons. So this gives the formulation of QCD. So interaction of quarks and gluons are through strong interaction, which is called QCD. And now the differential scattering cross-section is given in terms of these structure functions. I now denote them by F2 and FL, which are functions of both X and Q square. Now here, let me give a comparison of various interactions. I have taken this well-known table from the book by Halsden and Martin. So strong interaction, particles decaying through strong interaction usually have very short lifetime of the order of 10 to the power minus 23 seconds. An example of a strong decay is delta going to proton and pion. The typical cross-section here in units of millibarn is 10, and typical coupling you can assume it is of the order 1. This is a relative estimate. The range of strong interaction is of the order of 1 Fermi, you can assume. Then there is electromagnetic interaction. The range, as we all know, is infinite. Typical lifetime of a particle decaying through electromagnetic interaction is 10 to the power minus 20 to 10 to the power minus 16 seconds. Example is pi 0 going to gamma gamma. And the typical cross-section is of the order of 10 to the power minus 3 millibarn. And compared to the strong interaction, the coupling can be, typical coupling can be 10 to the power minus 2. Actually, the coupling, as we are going to see later, is not constant. It is a function of scale also. Compared to these two interactions, weak interaction is really weak. The lifetime of particles decaying through weak interaction is 10 to the power minus 12 seconds or longer. And the typical cross-section is much smaller. It is of the order of 10 to the power minus 11. So coupling is also quite weak. Now, the main difference or contrast between electromagnetic and strong interaction is given here. So suppose you look at the electron charge, you probe the electron charge, you have an electron surrounded by some other electrons and positrons. You probe the electron charge by going near the electron. So if you have a low energy probe, you cannot go very close to the electron. So you are at a distance from the electron. So there you actually effectively see a lower electron charge. As you go closer and closer to the electron, charge increases. Basically, you are penetrating this positron cloud and go inner and inner. So this basically is due to the interaction of electron and photon through QED. So there can be loops like this. So photons can interact via E plus E minus loops. And that is why this coupling increases or changes with distance in this way. So energy is inversely proportional to distance. So at large distance means smaller energy, small distance means higher energy probe. However, the situation is completely different in QCD, that is the color interaction, which is summarized here. Gluons, the mediator of color interaction, they carry color and interact with themselves. That is the main difference from the carrier of electromagnetic interaction. The photons do not carry electric charge and they do not interact with themselves. So because of this self-interaction, you can have gluon loops like this, which was absent in QED. And as a result of this, the color charge increases as you go away from the bare quark. As you go closer and closer, the effective color charge basically decreases. This is called asymptotic freedom. So the strong interaction QCD is somewhat similar to QED. You have this electron-photon vortex in QED. In QCD, you have this gluon-quark interaction vortex. So gluons carry color. There are three colors, quarks carry three colors, red, green, and blue. Gluons are bicolored. However, gluons can interact with each other. So there can be 3 gluon vortex and there can be 4 gluon vortex. So the observed particles, there are two types of observed particles. One group is called mesons, which are bound state of Q cubar. There are also hadrons. These are 3 quark states. These are colorless objects. Now, what I discussed in a few slides before is this parton distributions in deep inelastic scattering experiment. So this basically gives the nucleon structure in one dimension. What happens is that you have a target, you bombard it with a highly energetic electron beam. The target is a pancake, so quarks are frozen on the pancake. So this electron, you are basically seeing the quarks frozen on this pancake carrying a momentum fraction x of the proton. And the motion of quarks in the transverse plane ignored. As I said, these parton distributions are sometimes called collinear parton distributions. These are non-perturbative. They are extracted by fitting experimental data. The scale evolution of these parton distributions when you introduce gluon interaction can be calculated using Digg-Lab evolution equations. So this is well known. These parton distributions are independent of the process. Once extracted, can be used to predict cross-section of another process as the scale evolution is known. However, in this scattering experiment, one can also polarize the particle beams. So if you had doing an electron-proton collision experiment, you can polarize the proton in the longitudinal direction, or you can also polarize in a transverse direction. Similarly, in proton-proton collision experiment, you can polarize both beams either longitudinal or transverse direction. Okay, or you can have one unpolarized beam and one polarized beam. So these kind of polarized scattering experiment actually probes what are called polarized structure functions. So these play a role in understanding the nucleon spin puzzle. So what is nucleon spin puzzle? So we know that proton has spin half. So this spin half of the proton should be built from the spins and orbital angular momentum of the particles inside it. So that is, it should come from the intrinsic spin of the quarks. So quarks and gluons, we now know that they are not stationary. They are moving inside this nucleon. So there is also orbital angular momentum. So there is also gluon orbital angular momentum and intrinsic spin of the gluon. So the spin half of the proton should be consisting of all these 4 contributions. Now, EMC, European Muon Collaboration in CERN, in 1989 measured spin asymmetry in polarized muon proton scattering experiment and found that the contribution coming from intrinsic spin of quarks, that is the first term, is very small. That means significant contribution comes from gluons and as well as the orbital angular momentum of quarks and gluons. Unfortunately, it is still not very clear what is the exact contribution of the orbital angular momentum, although the polarized experiments have so far measured the intrinsic spin contribution of the gluon pretty accurately. There are various theoretical issues associated with this nucleon spin puzzle. Basically, the question is how to measure orbital angular momentum, what are the corresponding observables, can one really separate the gluon contribution into intrinsic part and orbital part in a gauge invariant way? And what is the connection of the experimentally observed gluon helicity distribution with the spin sum rule? So there have been a lot of theoretical work in the literature in the past decade, and most of these issues are have now been sorted out. So this is a separate research problem on its own. Now, let me go to another direction, that is how to measure the quark contribution to the spin. As I said, this is done in polarized electron-proton scattering experiment. So consider you are longitudinally polarizing both electron and proton, and you are basically measuring the number of scattered electron in your detector, and you are probing the case when the proton is polarized in the direction of motion versus when it is polarized in the opposite direction. And you can calculate or you can measure what is called the longitudinal spin asymmetry, which is given by or proportional to n up down minus n up up by the unpolarized cross section. And you can show that this longitudinal spin asymmetry is sensitive to the intrinsic spin carried by the quarks. So there are various experiments among those that I showed which can polarize this target or the beams. One is Hermes at DESY, one is Jefferson Lab, and then there is also this compass experiment at CERN, and there is also the RIC experiment. So RIC data has shown that there is significant contribution to the spin sum rule coming from intrinsic spin of the gluon. And this is the latest extraction of the gluon spin contribution by DeFlorian et al. In 2014. In addition to that, there are also several lattice calculations of quark and gluon angular momentum contribution. So there are different groups which calculate in different methods these contributions. I found that this article in this journal by Ke-Fei Liu gives a very nice summary of the present status of lattice calculations of proton spin decomposition. And the numbers that I quote here, I got from this article. According to majority of the lattice calculations, the status is that the total quark angular momentum contribution, that is intrinsic plus orbital, is 54 to 57%. Total gluon angular momentum intrinsic plus orbital is 38 to 46%, and quark orbital angular momentum is about 13 to 18%. This is lattice calculation. However, the question remains how to measure orbital angular momentum of quarks and gluons experimentally. There is an upcoming electron-ion collider to be built at the Brookhaven National Lab, USA. This will collide highly energetic electron beam with proton or heavy ion, as I said before, to take snapshots at high accuracy. And in this way, we can achieve a tomography of the nucleon. That is the aim. It will explore various questions related to the quark-gluon structure of matter, namely, how the quarks and gluons are distributed in space inside the nucleon, how do quarks and gluons bind together and form the nucleon, sorry for the typo, what is the origin of mass of the nucleon, that is, how do the masses of quarks and massless gluon make up the mass of the nucleon. Then, of course, the spin puzzle, how the spin half of the proton is made from spin and orbital angular momentum. It will also explore the correlations between spin and orbital angular momentum and intrinsic transverse momentum. In addition, it will also collide electrons with heavy ions and study how does a dense nuclear environment affect quarks and gluons and their interactions. So this is again a slide from Abhay's talk. This is the National Academy's assessment. So these are design parameters. It will be a high luminosity machine, and it is expected to have a broad range in center of mass energy between 20 to 100 GeV, and it is upgradable to 140 GeV. It will collide both unpolarized beams as well as polarized beams. It can have both longitudinal and transverse polarization of the proton, and it will have broad range in hadron species. There will be up to 2 detectors. So what exactly will this machine and other upcoming machines probe about the 3-dimensional structure of the proton? So the most general distributions inside the proton is given in terms of Wigner distributions, which are the Fourier transform, or what are called generalized transverse momentum dependent distributions. These are functions of 5 variables. First, you probe a quark inside the proton, which has a longitudinal momentum fraction x of the proton and transverse momentum kt, and you probe it at a impact parameter, transverse impact parameter bt from the center. So there are 2 kt, 2 bt, and 1 x. So bt, by the way, is not a conjugate to kt. Bt basically is the Fourier conjugate of the momentum transfer delta t. So this Wigner distribution gives the most general so-called phase space distribution of quarks and gluons inside the nucleon. From the Wigner distribution, you can get various other interesting objects which can be probed experimentally. If you integrate over this transverse position Bt, you get what are called transverse momentum dependent parton distributions, which are functions of x and kt, 3 momentum variables. and it gives a picture of the nucleon in 3D momentum space. If you integrate over KT, the TMDs, you will basically get the collinear parton distributions that I discussed so far, which are functions of X. On the other hand, if you integrate over the KT from these Wigner functions, you get a function which is a function of X and Vt, which are called impact parameter dependent parton distributions. These are the Fourier transform of what are called generalized parton distributions. These can be proved in so-called exclusive processes. If you integrate over X, you get Fourier transform of form factors. So there are many references which discuss the Wigner distributions in detail. There is lots of interest in this kind of generalized distributions in recent days, because it has been shown that they can give a unique idea or some idea about the internal correlation between the intrinsic transverse momentum and spin of quarks and gluons. Are there any questions so far?
Good. Good. Okay. Yeah, I think we're good.
Okay. So now let me come to the main topic of my talk. This is the transverse momentum dependent parton distributions that I just introduced. Where do you see this transverse momentum dependent parton distribution or TMDs? Experimentally, people have observed very large, that is about 30 to 40% single transverse spin asymmetries in experiments. What are single transverse spin asymmetries? So you do a polarized scattering experiment, like you bombard proton with proton, you polarize one of the proton beams in a direction transverse to its motion. And in the final state, for example, you observe one particle, say a pion. So as you see in this picture, so single transverse spin asymmetry is defined as d sigma up minus d sigma down divided by the unpolarized cross section. So the numerator is non-zero because it turns out that the cross section for this process depends on whether the proton is polarized up or proton is polarized down. And you see from this plot, which is from Fermilab in 1991, you see that this asymmetry can be quite large, and it also depends on the charge of the pion. And this kind of large asymmetries cannot be explained in terms of collinear leading twist parton distributions. What were we doing in collinear parton distributions? We were assuming, so we can look at this picture, we were assuming that the proton is basically a pancake and the quarks are frozen on this pancake. So this virtual photon is basically probing a quark at a longitudinal momentum fraction x. That does not explain this single spin asymmetry. Namely, we cannot assume that these quarks and also gluons are frozen in this pancake. They can also have some transverse momentum. We have to incorporate the intrinsic transverse momentum of these quarks and also gluons in order to explain these single transverse spin asymmetries. The other way to explain is twist 3 parton distributions. I won't get into that. So transverse momentum dependent parton distributions are functions of X and intrinsic transverse momentum. It gives a 3-dimensional picture of the nucleon in momentum space. As we are going to see, this gives correlations of spin, orbital angular momentum, and KT. These transverse momentum dependent parton distributions play a role in processes where you observe 2 scales, or you have 2 scales, one large scale and one small scale. 2 such well-known examples are semi-inclusive deep elastic scattering, that is an electron-proton scattering, and in the final state, in addition to the scattered lepton, you observe a particular hadron with a given transverse momentum. So these 2, incident and the scattered lepton, form a plane, which is basically called the lepton scattering plane. Compared to this plane, the final hadron makes another plane. And then if the target is transversely polarized, then another plane you get from there. So these are the azimuthal angles phi s and phi h, which are measured from the lepton scattering plane. The other example is drell-ion scattering. So you collide proton-proton, and in the final state, you observe a lepton pair with definite transverse momentum correlations. In these 2 processes, the TMD factorization is proven to all orders in alpha s and leading twist. There's quite a lot of references. For some other processes, attempts have been made to prove TMD factorization at 1 loop and beyond leading twist. Now, if you want to write down the cross-section of deep elastic scattering versus semi-inclusive deep elastic scattering, what is the major difference? So this is the schematic diagram of semi-inclusive deep inelastic scattering. This is the final state cart, and this is the final state hadron. So here, since there is a hadron in the final state, in addition to xb, the x Bjorken variable, there is a zh, which is defined as the momentum fraction of the hadron with respect to the virtual photon. In deep inelastic scattering, when you do not observe the hadron in the final state, you probe collinear parton dynamics. So the cross-section is given in terms of the leptonic tensor L mu nu and the hadronic tensor W mu nu. Whereas in semi-inclusive deep inelastic scattering, differential in this pH square, you probe transverse parton dynamics. So here you have the L mu nu lepton tensor, but the W mu nu now depends on all these variables, including the hadron moment. So the leptonic tensor in DIS and semi-inclusive deep inelastic scattering can be calculated perturbatively. The hadronic tensor is non-perturbative because hadron has structure. So in deep inelastic scattering, the leptonic tensor, hadronic tensor can be written in this way in terms of the current. And these are some kinematical variables. So as we saw before, these can be written in terms of two structure functions, which are functions of x and q square. So here I have written them as f1 and f2. So they basically can be associated with the longitudinal and transverse polarization of the virtual photon. When the proton is polarized, this is for unpolarized deep inelastic scattering. When the proton is longitudinally or transversely polarized, we get longitudinal and transversely polarized structure functions in addition to them. For semi-inclusive deep inelastic scattering, this is the process. And here the hadronic tensor has a few more structure because you can form some more tensors of the available vectors. So there are at leading twists, there are all these 5 structures. And this hadronic tensor can be schematically written in terms of 2 functions. One is called phi, the other I have called delta. So phi is called the quark correlator, which is parametrized in terms of the TMDs, and delta corresponds to the final state. For final state, the hadronization is also a non-perturbative process. So this is called a fragmentation process, and the function is called fragmentation function. And this semi-inclusive deep inelastic scattering process basically probes a convolution of these TMDs and the final state fragmentation function, as we are going to see later. So each of these convolutions, each term has a convolution, each term in this expression has a convolution. They come with a different weight factor depending on the azimuthal angle. So this weight factor is given by this function W. And this quark correlator is parameterized in terms of the various TMDs. And this is the parameterization of the quark correlator. When we integrate over the transverse momentum, the collinear correlator is parameterized in terms of 3 structures. These are the 3 collinear parton distributions, the unpolarized, longitudinally polarized, and transversity distribution. Each of them come with a different tensor vector structure. A TMD correlator is parameterized in terms of these TMD functions. These are the TMD distributions. There are all these different TMD distributions, and each of them come with a different tensor structure. These are that I have listed here are so-called leading twist contributions. So how to extract these TMDs from experiment? So as I said, in semi-inclusive deep inelastic scattering, what you do is that you basically can extract quantities that appeared in my expressions before. Those are these coefficients of different structures. So these are the quantities, the coefficients that can be extracted in experiment. So each of these coefficients, the structures, have a different angular modulation. And these angular modulations are extracted. This angular modulation basically comes from these kind of tensorial structures. So these structures involve convolution of 2 different TMDs. One is a TMD distribution, one is a TMD fragmentation function. Like this structure, UUT, when you have this unpolarized probe and unpolarized quark, you probe basically F1, D1, both unpolarized parton distribution and unpolarized fragmentation function. The cos 2 phi type of modulation probes a convolution of what is called the Bohr-Mulder's function and the Collins function. And similarly, the sine phi h minus phi s kind of structure probes the Sievert's function and the unpolarized fragmentation function. So by probing different kind of azimuthal modulations contributing to the semi-inclusive deep inelastic scattering, you can get information on various TMDs. So these cross sections, let me come to semi-inclusive deep inelastic scattering in a bit more detail. These cross sections are written in terms of this TMD distribution and fragmentation function in a factorized form. This is called the TMD factorization. Okay, so there are these TMD PDFs. Then there is the scattering of the lepton with the quark, that is the hard scattering that you calculate perturbatively. And then there are these TMD fragmentation functions. As we are going to see, these TMDs play an important role in single spin and azimuthal asymmetries. However, the downside is that these TMDs depend on the process due to what are called cage link or Wilson line in the operator structure. So when we discuss the collinear parton distribution, we said the basic predictive power of the theory comes because these collinear parton distributions are independent of the process. You extract these collinear parton distributions from a process, you can use the same collinear distribution to predict the cross-section of another process. However, this is not true always for TMDs because TMDs have this kind of structure. The operator structure of these TMDs has this form. And to make this kind of structure gauge invariant, you need to insert a Wilson line or gauge link. And this gauge link for TMDs have this kind of structure. It's a line, it is exponential of line integral of the gauge field. And the bilocality of these operators here is in longitudinal as well as in transverse direction. So gauge link is nothing but the resummation on initial or final state gluon exchanges. And that is why these gauge links are process dependent. So we will discuss more about the process dependence of TMDs later in the context of Sievert's function. But let me come to the different quark TMDs. So at leading twist, there are 8 quark TMDs which are given in this table. So along this line, this is the polarization of the quark. This is the polarization of the target. So there is the unpolarized distribution, there's the longitudinal distribution, there's the transversity distribution. And these are the 3 distributions that survive if we integrate over the transverse momentum. There are 2 TMDs. This is called Sievert's function and this is called Bohr-Mulder's function. They're odd under time reversal. And as I said before, different TMDs contribute in different azimuthal modulations. So TMDs are also to be extracted from experimental data. There is quite a lot of progress in the extractions of TMDs from data for unpolarized quad TMD as well as the Sievert's function. There's a lot of references here. I have cited only a few of them. This is a pictorial representation of the TMDs from the lecture notes by Alessandro Bacchetta to understand the meaning of various TMDs that I showed in the previous slide. So this black arrow shows the nucleon with transverse or longitudinal spin. So here we will assume that the nucleon is moving transverse to the plane of the slide. Okay, and the polarization is in the plane of the slide. So if it is round like this, so it is longitudinally polarized, and if it is an arrow, it is transversely polarized. So the red denotes the polarization of the parton, and the blue arrow means the parton transverse momentum. So if we probe an unpolarized quark inside an unpolarized nucleon, it is F1. This is the helicity distribution G1, longitudinally polarized quark inside a longitudinally polarized nucleon. Transversity is a transversely polarized quark inside a transversely polarized nucleon. The Sievert's function basically gives a correlation of the transverse momentum and spin of the target. Here you are probing an unpolarized quark with some transverse momentum inside a transversely polarized target. The Bohr-Mulder's function probes a transversely polarized quark with transverse momentum inside an unpolarized target. And these two are known as Wormgier functions. They also probe the spin and transverse momentum correlations. And this function is called Pritzilosity function. This probes a transversely polarized quark inside a transversely polarized proton, but unlike transversity, these transverse directions are orthogonal. So each of these TMDs give different important information about the spin and angular momentum correlations inside the nucleon. Similar to parton distributions, there are also TMD fragmentation function for the final state hadron. So at leading twist, there are this set of TMD fragmentation function. The general structure of the TMD fragmentation function is given here in terms of this operator structure. This is the final state. And there is also gauge link involved in these states. So to give a little bit more idea of the TMDs, here I discuss one of the TMDs, which is the Sieverts function. So Sieverts function TMD was first put forward by Dennis Sieverts in 1990. This is related to the probability to find an unpolarized quark inside a transversely polarized nucleon. It includes the correlation between the quark intrinsic transverse momentum and the transverse spin of the proton. And in some models, it is shown to be related to the orbital angular momentum of the quarks. As we are going to see, it is a T-odd function, and it is important to consider the effect of the gauge link or Wilson line for such functions. If you do not consider it theoretically, you will basically get a zero Sieverts function. Now, in terms of these TMD functions, the cross-section for semi-inclusive deep elastic scattering, the differential scattering cross-section, can be written in this way. And as I said before, experimentally, what one measures are these coefficients which appear together with some particular azimuthal modulation. For example, if UU cos phi h is the coefficient of a cos phi h term in the cross-section. And it is this coefficient of this sine phi h minus phi s that is of interest. This is called the Sieverts asymmetry. This kind of asymmetry in the structure is sensitive to the Sieverts function. So each of these functions is sensitive to a different TMD. Sometimes the same function can be sensitive to several TMDs. So this brings me to the end of my first talk. In the next talk, I'll talk a bit more on the process dependence of TMDs, TMD factorization. And mainly, I'll introduce the gluon TMDs because the other talk will be mostly on gluon TMDs. I'll talk about how to probe gluon TMDs in heavy quarkonium production, for example, at the upcoming electron-ion collider. And I'll also give an idea of some of the recent parameterization of the TMDs and how to estimate asymmetries in the kinematics of the upcoming TMDs, EIC. And I'll also discuss the scale evolution of the TMDs and how does it affect the spin asymmetries and cross-section. Thank you.
Asmita, that was fantastic. I honestly think the best introduction to standard model and hydrogen nuclear physics that I've ever seen.
Thank you.
Questions from the floor or from the I know Nia at least is also online. Yeah, questions from the floor. Yeah, Daniel, please go ahead.
Yeah, just one thing. Maybe you said it and I didn't quite understand. When you're talking about the process dependence of the TMDs, and you the fact that it was due to the fact that you have to include Wilson lines for the gauge invariance. I don't think I fully why the inclusion of the Wilson lines here makes it process dependent. What is it about it that causes that?
Yeah, so I will actually discuss it in the next talk. What happens is that this Wilson line is a resummation contribution of the gluon exchanges between the soft part and the hard part. And how these gluons will exchange will depend on the process. For in semi-inclusive deep elastic scattering, these kind of things basically come from final state interaction. Whereas in Drelian scattering, we'll see that these come from the initial state interactions. These are just two examples.
Yeah.
So that is what, when you resum them, so that resummation result then will depend on the process.
Okay.
But we will discuss it in detail in the next talk.
You don't lose, well, universality completely. You just chop your process into.
That's right. It is a calculable process dependence.
Okay.
Good. Other question? I wanted to ask, maybe chair's prerogative. You mentioned the model dependence of I made a note of the Sieverts function. Could you talk a little bit about that? And I think we have a similar issue in heavy ion physics and energy loss physics, where at the end of the day everything's QCD. So in some sense, that's not a model, but that I guess at some point you're not able to actually do QCD, so you make some kind of simplifying approximations, and then that introduces in some sense, a model dependence to a measurable quantity.
Yeah, so what I mentioned was that in some model calculations of Sievert's function, it can be shown to be related to orbital angular momentum contribution of the quarks. So there are a class of models where you can show a connection between Sievert's function and the orbital angular momentum, but it cannot be shown in a model independent way.
So this is on the interpretation side, in other words.
Yeah, so some assumption in the model is basically important to make this connection.
Okay.
Because I guess I'm also sort of struggling in the sense of, for certain regions of, I guess, phase space, the quasi-particle picture of a parton, a quark, or a gluon is well defined. But if you start to get to lambda QCD-ish type scales, then that picture fails. So, when you motivate it in terms of the spin puzzle of the proton, how much of that spin is coming from, call it non-perturbative physics, and how do we think about that?
Yeah, so spin puzzle is mostly non-perturbative physics because this come from the quark and gluon distributions.
Yeah.
So this helicity distribution, even orbital angular momentum distribution, these cannot be perturbative. What you can calculate perturbatively is the scale evolution. So in this spin sum rule, nucleon spin is half at any scale.
Right.
But the quantities on the right-hand side, each of them are scale dependent. So how they evolve with scale, that you can calculate, but the quantities themselves must be non-perturbative.
Tricky thing to think about.
Yeah. That makes a lot of sense. That's actually really very nice. Super. Maybe any last questions for Asmita? If not, well, thank you so much. That was really great.
Thank you. Bye. I'll see you next week.
Yeah, if you could please send your slides to us, and we'll add them to the video.
Yeah, I will send the slides to you.
Awesome. Thank you so much. Have a great week.
Thank you. Bye.
Thank you.